So the vector is basically this magnitude right here, or this direction. A, B, and C, like you see on the screen. And vector loops have the meaning that essentially we end up right back to where we started. So we come back this way, right? So it means it has to create a full loop. And that makes sense, right? Because for a mechanism, if we have like some sort of mechanism, I don't know about you guys, but I don't know many mechanisms that don't loop back to the beginning. Right? Like, what would be the point of making a mechanism that, like, once it is done, it's done there forever? It doesn't come back. You see the point? So, I don't know many mechanisms that do that. I think basically all of them that we use they come back to where they start, which is what we want. We want it to come back to the start because the only way that a mechanism can continue to go over thousands of cycles is that it has to come back to the start. So that's what we're looking at in this chapter. We are aiming to create vector loops. And so we are aiming to create those. And this is, like I said, the hardest part of this chapter, is because vector loops can be created in a variety of different ways, but how the simplest way to make them will make your life easiest. But the problem is that it's hard to determine what is the simplest way, right? Which we will talk about and you'll see in a little bit. So I'm going to do a little bit of reading here. Let me pull out the highlighter. Never used it before. We'll see how that goes. So it says, this chapter introduces vector loop method for position analysis of mechanisms. The vector loop method is also referred to as loop closure method. Position analysis is a necessary first step before one can initiate velocity and acceleration analysis of a mechanism. So I mentioned this on Friday as well, that velocity and acceleration analysis obviously are derived from the initial position, right? Because all of you, I'm sure, know about your calculus that, the first derivative of position is velocity, and then velocity's derivative is acceleration, right? So it's all derived from the very first one. And then it says, in the next chapter, we will delve into velocity and acceleration analysis using kinematic coefficients or influence coefficients. So basically, in the next chapter, which is the third exam, you will be doing the velocity and acceleration analysis. But in this chapter, all we are doing is making the loops. So, vector loop approach involves summation and subtraction of a number of connected vectors. For this reason, we first give a brief review of vector addition, then follow up by the application of vector addition to position analysis of planar mechanisms. Consider two vectors A and B, which is right here on the screen. So, A or C is equal to A plus B can be found using the triangular or parallelogram summation method as shown in figure 1. So what it's saying is that if you take, let's get a different color. If you take the vector A and you add vector B to it, C has to be equal and opposite to it, right? Because if this is to be equal to 0, which it is to get back to this point, it has to be equal and opposite to it. And so that's basically what we're doing in these vector loops, right? Is that if you have, a vector that like goes here and then up and then around and then down and up and into here or something like that, basically all these vectors have to be equal to 0, right? I just kind of drew you some, random directions, right? But they have to all be equal to 0. Or some of them have to be equal to the other ones added together, right? So there are some, negative ones and some positive ones. All right. And I'm sure, I think you guys probably remember this right here. Hopefully. Because you did do this in a class previous, I just don't remember which one. I think it's the resultant, right? Whenever you do, A and B and you get C out of it. But, anyway. So then it says, we will focus on triangle method of vector summation. The vectors A and B are arranged in a sequence such that each appear at the termination of the previous vector. Any sum can be viewed a vector loop. The vector equation a plus b equals c can be written as a plus b minus c equals 0. If one traverses the loop ABC in a sequence along vector A, then B, then return along vector C, or negative C, the net traversal is 0, consistent with the equation A plus B minus C is equal to 0. This fact leads to the result that if one traverses any vector loop and properly adds the vectors traversed, then the result should sum to 0, since upon returning, no net displacement is achieved. So that is something I mentioned Friday, is that it's that term displacement right here. So displacement is basically it's where you started and where you ended up, right? So in like whenever the term was first introduced, they would use like city blocks, right? So if I went one block this way, one block down, right, my displacement is the distance from where I ended up here to where I started, right? That is displacement. But if I did this, if I went here, 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 and then back to the start, it means that my net displacement was 0, because I ended up, even though I walked this whole square, right, I ended up right back to where I started. So distance and displacement are different, right? So the distance I walked would be this, city corner, right? But the displacement would be 0, because I ended up right back to where I started. Hopefully that makes sense. Alright, and then it says, therefore, the vector loop equation for the vectors shown in figure 2 may be written as follows. Start from the crosshair and traverse along A, then B, then C, minus D, then E, F, G, minus H, minus K. Our action results in a net zero displacement. Therefore, the vector loop equation is this. So this is what they did. So this is their vector loop equation for the following figure right here. So they started at A, which was this crosshair, and they went up, there, down, over, and now here, this is the trick though, right here. So, just so everyone is aware, that in this class, when the arrows are going opposite to the direction, so like so right here, these are all positive vectors, because the arrows are pointing in the direction we're going. So like A goes this way, B goes this way, C goes this way. When it goes opposite to that, so D is going opposite to that start, right? It's going back into the previous vector. That is a negative vector, and you can see it shown right here. And then E is positive because it is going with the original vector, as you can see. F is positive, going with the original one. G is positive, H is negative, right? And K is negative, because they're going back into the direction of the original vector. And so that is represented right here as H and K. So basically, does everybody understand how to read these vector charts, or this vector drawing? Like if I gave you something like this, could you give me the correct equation? Yes or no? Okay, because it's sort of important for you to make sure you know this. Like basically you have to follow the arrows. If the arrows are going, so you start with A, you go here, 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 and then once you reach an arrow that's going back into the first one, so you see like right here, once you get to an arrow going back into itself, this one is going with the original direction, right? But this one is going back into it, which means that vector D is a negative vector. Negative D, right? Because it's going back into the first one. Why is it H negative K? What do you mean? Why is H negative K? Or why are they both negative? Is that what you're asking? G minus H minus K. Oh, okay. So you're asking why is it subtracted from it? So this will be something that I talk about in a minute. But essentially, what it is showing here is really fast, Jackson, is that it's just showing that these are negative quantities, right? But you're saying that if you subtract k, which is negative, you would turn it to positive. Is that kind of what you're going with? Yeah. Okay. So we're gonna talk about that in a minute, but just right now. So just how about this? For right now, Jackson, just know that these are placeholders just to show you what direction they're going in, right? But we're gonna get to that in a minute. It's a little confusing, and I never got a really good answer when I was doing it, so we'll talk about it, what I expect from you in that part. But yeah, I agree with you. But if you think about it in mathematical terms, is that like if you just put like if you added every one of these together, right? Like let's say you added a through k together, but k was a negative vector, you would still get 0. You would, or like all the negatives were still negatives, and you just had a plus sign in front of them, but you knew those vectors were negative, you'd still get a 0. So I think it's just has to do with like the operation in front of it, but I don't know. We'll talk about it more. So then right here it says if we limit the space to two-dimensional space x and y, then two equations will result from the vector loop equation. We refer to these as scalar equations or just equations. Each of the x and y projections of the above vectors must also satisfy equation 1, which is here. So what it is saying here is that if you take this vector, so let's pull A out right here, guys. So let's pull A out. So A is sort of like this, right? And what we're saying is we are limiting this vector into x and y only. So can somebody tell me what the x equation of this vector looks like, vector A? Or how would we find it? Let's go with that. What would a x equation of that look like? It's the same way you would do it on a unit circle as well. You know, like the unit circle where it's like, say you had this going. What is the x component of this, and what is the y component of that? Anybody? So the x component of this is what you would think it is, right? It is a, or vector A, cosine of theta A, right? So it's basically, it is the x component of it is using your cosines and sines, just like you would in other classes, right? When you were trying to find the x and y components of things. So this is where the fun begins, is that for this vector loop, the one that I have pulled out right here, this vector loop, your two equations that you get from this would be the following. It would be this whole equation written in terms of cosines equals 0, and then it would be this whole equation written in terms of sines is equal to 0. So it would be like a cosine theta A plus b cosine theta b, etc., the whole way around. Then you would do it with sines, and those are your two equations you get from it. And so the importance of the two equations is that when we get to do velocity and acceleration analysis, is that you have to have it makes sense in here too. So actually it starts from here. Never mind. So scratch that. Essentially, when you create this vector loop, I mentioned this on Friday, is that you have to have the correct number of unknowns in equations, right? Because we can't solve, you can't solve a question that has, 6 unknowns and, you have 5 equations, right? Because one will always not be able to be found. And so you have to, by using these vector loops, you're trying to get the correct number of equations and unknowns. And now you might be wondering, well, what is unknown and how would we know if something is unknown, right? we are about to get to that, so hold on to that thought. So right here, we're moving on to position analysis of a mechanism. So it says the vector loop approach can be used to obtain the equations governing the position of a mechanism in two-dimensional space. The approach is most suitable for closed chain mechanisms, but is also applicable to open chain mechanisms. Consider the 4-bar mechanism shown below. In defining a vector loop of the 4-bar mechanism, we must make use of constant links on each link of the mechanism defined by the distance of the centers of the revolute joints. So, this is how you do it. So essentially, if you look at this question right here, this right here, let's call this 1, right? And obviously this is link 2, 3, and 4, right? So if you were to make a vector loop of this right here, how would you do it? How would you do it and to make it to be, it's a closed loop, right? We need it to come all the way back to 1. How would you do it so that the motion of this is always defined? So like if I took this thing and you went woo and spun it this way, and then the whole machine came over here, right? How would you draw this in order for it to be a closed loop? Because that's what we need, right? And that the motion of this is defined as it turns anyway. So where you would start is that you would take this first link right here, right? Which is a revolute joint, which is what they're pointing out here, is that these are revolutes. The very basic way of making this is you're supposed to follow the revolute joints. Follow the revolute joints together. Because we know so this is where you guys have to use your thinking caps for a second, is that, so these links are known to us. So link 2, the center of the revolute joints is known to us. The center of this revolute joint is known to us, and the center of this one is known to us. And the reason why it is known to us, so you might be wondering, well, we don't know this length, right? There is no L3 is equal to 10 up here, right? But the reason why we know it is because we've created the machine, right? So we know these parts lengths, right? These are known quantities because we know them. We made them, and we know we can measure that. We could go out to the machine shop and measure this length, right? So those are known quantities to us. And then there's one here as well. To close the chain, you have to connect these two grounds. And that is another principle of doing these vector loops is that a lot of times whenever you get to like the far side of the mechanism, a lot of times it goes right back to the beginning, straight through. And also we do know this as well, because essentially if we're hooking these two parts up to grounds, those grounds are not moving. They're not changing distance with respect to each other. Therefore, we know that distance as well. So probably someone in here is wondering, well, if we know all the links, then what is unknown in this, right? Am I onto something here? Maybe someone's wondering what the hell are we even looking for, right? What are we looking for? Anybody want to take a stab at what we're looking for here? What are the unknowns in this right here, in these links? So think about it in terms of vectors, right? So when you draw this loop, let's say it's like here, 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 and, here, right? What is unknown in these vectors? As this thing moves, so let's say we turned this way. This link now becomes straight up and down, and then the whole machine moves to the right side. It goes clockwise to the right side. What is unknown? Anybody? Think about it in terms of what I did earlier with the vector, right? So I did this vector, and I did, let's put it in terms of this question here. How about this? So if I wrote out the x and y component of 2, it would be R2, because that's how we're going to denote vectors in this class. R2 cosine theta 2, and then R2 sine theta 2. So in this right here, in this little breakdown here, which is you guys are going to have to get familiar with this. That right there is the component of link 2. Link 2's components are right there because it's only an x and y. So those are the x and y version of what link 2's vector is doing, right? So what inside of that those two little equations are unknown. Theta, correct. Because R2 right here, we know that because it is just this length, right? We know that length, we know 3's length, we know 4's length, and we know 1 to 1 over here. We know that length. But theta we do not. Because at all times during this like motion, right? So like let's say it's this right here. Let's say that's theta 3, right? If that's theta 3, as this thing moves, so let's say that this now, instead of being like this, right, this R2, so let's say R2 is that. Let's say we turn it, and now R2 is basically standing straight up, and then one is coming off of it, and then the other one is basically straight down of it too. Because if you stood R2 directly upright, you would almost have a square, right? Essentially it would look kind of, it would be a lot more square-like than it is now, right? So that means that theta 3 has now changed, right? It is no longer the same as it was before because that angle opened up, right? It became wider. So theta 3 is an unknown. That is one of our unknowns of this. And likewise, theta 4 is also unknown, right? So which would be something like this. Right? And so the whole point is that you just need to you need to know how many knowns and unknowns there are in your question. And that is the difficult part of doing this chapter. So let me zoom out again really fast and get back to back here. So let's get rid of that. So what they did is, as I showed just a second ago, they showed this vector loop, right, which is what I created. Theta 2 they drew right here, so it is it's the theta between this part and this right here. And now you guys we'll talk about something in a second, but essentially this is what we've drawn, right? And this right here is theta 3. Theta 3 is the distance between R3, and they keep the x-axis right here, which I highly suggest you do. I always forget to, but the x and y axis is here. And now you guys might be wondering, well, wait a minute, like why is it tilted like that? Right? Why did we tilt the x-axis like that? The reason why we tilted it like that was because using the x-axis in that way eliminated an unknown for us. It helped us a lot, and the reason is because R1 here. R1, this vector 1, if you draw this straight, straight across it, R1 has an angle with the x-axis, right? But if you draw this vector straight through this connecting line down here, so if you draw this line straight through here as the x-axis, R1 doesn't have an angle anymore, right? Because all angles are taken with respect to the x-axis. Therefore, what is the angle of R1 when it is directly on the x-axis? It's 0. And so drawing your coordinate system like that can help you out. And so this is another tip. So if you're going to write these down, another tip is that you should make the x-axis work or make your coordinate system work for you in the best possible way. you need to draw it in a clever way to try and eliminate something. And generally, it's pretty obvious what you should eliminate, right? Because a lot of things look like this. They have like a big line that's, straight here, and you can just draw it on that. But some of them require a little bit more intricacy. And so you have to be clever in sometimes whenever you create these. And so if you look here, our unknowns are theta 3, theta 4, theta 1 is gone because we know it now. And theta 2 you would say is unknown, but theta 2, I told you that theta 2 is your input link a lot of times in this class. I think most times, actually, basically every time, is that this is your input link. So if we are the one changing the angle, because we know that we're inputting some sort of angle change on it, we know what the angle is. And so theta 2 is always generally known as, it's something that we know. So for this question, there are two unknowns. But we're going to talk a little bit more about that in a second as I go through the rest of this. So this is vector loop applied to a 4-bar mechanism. So it says, note that figure 2b, which is this one right here, this one is one sec. Here for that applies, only one variable needs to be specified to fully describe. Yeah, okay, so this is something for the previous chapter. So right here, they're talking about what I just said. So figure 3c, which is this right here, illustrates that a coordinate system xy is attached to the mechanism. A convenient choice is to let the x-axis connect the centers of the two elements on the ground link, and y is chosen normal to that. All angles are defined with respect to the x-axis as shown. Since the centers of the revolute joints on each link define the stationary points on the link, vectors are defined and numbered according to the number assigned to the link. As shown in figure 3c, vector r1 defines the distance and orientation of the two revolute joints on the ground. Similar locations of the other links are r2, r3, and r4. These vectors form a closed path, so their combination must yield 0 since it would return 1 to the starting point. Traversing the loop from the origin along r2 minus r3 minus r4 minus r1, we can write the following vector loop equation. So this is their equation for the question. So if we go back up here, this is what they said. They said that if you traverse this, they have, you go R2 to R3 minus R4 and minus R1. And that is how they create the vector loop. Now at the end of this, we will talk a little more about how I want you to number these and how I want you to do them. But for now, just use that as sort of your example. So, and then it says, any projections of the vectors in equation 2 must satisfy the same relation. That is, if we let subscript x and y represent the two projections of the vectors x and y axis on the coordinate system shown, then the following equations must be satisfied. So what they are doing here is, this right here is your x and y equation. So let me write that. So this right here is your x version and your y version of that same vector loop. So you take this vector loop and you just make x and y versions of it. So it should go r2x plus r3x minus r4x minus r1, because that is simply how this went, right? It was r2, r3, r4, r1. And you just put y subscripts attached to them, right? And the reason you do that is because then, from there, you make the scalar equations, which are the ones we talked about earlier with cosine and sine, right? Which would then, you, instead of taking that r2x and r3x and r4x and r1x, you implement where the x is, it's the cosine theta of whatever angle you're on, right? So instead of r2x, you have r2 cosine theta 2, or r3 cosine theta 3, So basically here, you go to that, you go to that, and you go to that, right? And here as well. So essentially R2 becomes R cosine theta 2, R3 cosine theta 3, R4 cosine theta 4, R1 cosine theta 1. And then, so does everybody see how that works out right now before I keep going? These are just the x and y components of that vector loop, right? That is all they are. Nothing more than that. So, let me go ahead and get rid of this. So real quick, then the next part of this is to eliminate things that you already knew or that they eliminate themselves. So because, if you recall, we drew our coordinate system in that odd way like this, you know, where it was like y and x, if you remember that, up here. Because the x and y went here, and it's right on R1, which makes theta 1 equal to 0. Because of that, we can get rid of this right here, right? So what is cosine of 0? Cosine of 0 is 1, therefore we can get rid of cosine of 0 and just put 1 times R1, right? But then similarly, when you do the other one, you have R1 sine theta 1. What is sine of 0? Sine of 0 is 0, which means that this just goes away. So you have to then just eliminate things that you already knew, right? So to here, and then to here. And so it made your equations just a little bit easier. All right. Alright, so then the next part is basically what this is telling you is that if you would have chosen a different direction, right, of vectors, so if you would have chosen a different direction of vectors, you would essentially get the exact same thing, right? Because all you're doing is you're just taking, you were just setting up the equation and you were getting rid of unknowns or known things at the end of it. So if you did different vectors, right? So for example, they set up their angle 4 to be here, right? Which I think they did it differently before. Let me go look. Yeah, so they set up angle 4 to be down here instead of up here. And then they did this time, they put theta 3 in the same spot. They kept theta 4 here because remember, theta 4 or thetas are taken with respect to the x-axis, and then theta 1 is still from here to here, right? So essentially, doing it a different way will lead you to the same result a lot of times. It just shows that you have to number them appropriately, right? You just have to know what you're dealing with. And what I mean by that is you can't go like this. You can't do something like this, because then you'd go like theta 3 here, which is good, and then if you did theta 4 here, which is good, and then if you tried to do something like this, you know, theta 5, and then you did theta 1 here, you know, across it. Essentially, you're just adding things that don't need to be there, but you can still write it like this. You'll just have to come up with an additional equation, and theta 5 will be part of it. It's just basically you just have to be careful you're not just over defining things, right? And just don't over define things. And the reason why you don't have to put an angle here, so real quick, this is something you have to know just from geometry, is that the reason why you don't have to put an angle here. So like, why don't we have to put theta 5 there? Well, the reason why we don't have to put theta 5 there is because this is basically it's a four-sided figure, right? What do the angles on the inside of a four-sided figure have to add up to? Anybody? Rosendo is correct. It is 360 degrees. So, theta 2 plus theta 3 plus theta 4 plus this down here have to be equal to 360. But there's a reason we don't have to do this one. It's because theta 2 is something we know already, right? Because it's the input link. So real quick, I'm going to write this over here. So input. We treat it as something we know, right? So it's the input link. Theta 3 and theta 4 are unknowns, right? I think everyone can agree with that. So if theta 3 and theta 4 are unknowns, and from this vector loop we get two equations, right? That means we can solve this, right? We'd have two equations and two unknowns we could solve. And if I found theta 3 and theta 4 using those equations, what does that mean? Theta 2 plus theta 3 plus theta 4 minus 3, or what is it? 360 minus that has to be equal to that last one right here, right? Essentially, the addition of all these angles have to be, and you subtract, or 360 minus those angles gets you this last one here. So you don't have to name it because it's something we will know in the end anyway, right? Does everybody see kind of how that makes sense? Is that basically because we know those other three, due to two of them we solved the two equations and two unknowns for, and the other one we know at the beginning, there's no reason to name that other one down there because we will know it at the end anyway, because it has to be the difference between 360 and the total angle summed up. So there's no reason to name that little angle in between as something, because it is something we already will know. And this is something you have to understand for other ones, or a lot of people, they would make, so this is where a lot of people went wrong, is that they would just over angle things, over define things. They would end up where at the end of their drawing here, they'd have like, on a four-sided figure, they'd have 6 angles, right? For some strange reason, they would make 6 angles, and then they'd realize, they're like, well, wait a minute, I only have 2 equations and like 6, or 6 unknowns or something. I can't solve it. Well, it's because they were just defining things just to define them, right? Even though they were something we didn't need to. So basically, you have to have a little bit of geometry in your wheelhouse to understand that some things, you'll see these a lot where it's like a triangle. You'll go, oh, well, this is the input link right here, right? So theta 2, theta 3, and we do not need to know this angle right here. Because theta 2 is known, theta 3 will solve from the equations. This angle right here is something, once you know theta 2 and 3, the third one is trivial, right? You know what it is just based on it has to equal 180. So there's no reason to name it. And if you do name it though, so let's say you did do that. Let's say you wanted to name this, right? You would just have to write an equation such as theta 2 plus theta 3 plus theta 4 equals, what is it, pi, right? Or something like that. You would just have to write that. And because, now real quick, since you wrote that equation out, remember, so how we're doing this is you're writing this such as a way you would be able to solve it through a computer, because I'm not going to ask you to find any of these because that's a lot of math. A lot of these takes there's like 6 equations and 6 unknowns. So you aren't going to be solving these. But if you wrote this into a computer and you defined theta 2, theta 3, and theta 4, but you didn't have an equation for theta 4, because from this you would only get 2 equations, right? So you'd have 2 equations, 3 unknowns, right? For the most part. Let's say one of these R's is, let's say one of these links is not known. You would have to, I'm giving you a situation that might show up in this class. One of these links might be unknown. And so the problem is that now you have 3 unknowns and 2 equations. And so if you add this equation, you now have 3 equations, because this equation, while written into a computer, would go, oh, well, since we know theta 2 and theta 3, theta 4 is derived from that if you subtract pi off. See what I'm saying? So what I'm basically the overall thing is that you have to know a bit of geometry and use a little bit of sense to understand that there are some things you do not need to define because they will be known at the end of it anyway. Over defining things is dangerous, and a lot of people in here over define things because they think that every single angle, every single length needs to be defined. It does not. Not always. Alright, let me see. So real quick, it said the above equation, so this was back to the original thing, is that it says that these equations, when done a different vector loop way, get you the same result. And that's it. Basically, it just all it did was reverse the it just reversed the signs, so it's not a big deal. And so then it says equation 8 contains 3 variables, which equation 8 is right here. Equation 8 contains 3 variables, theta 2, 3, and theta 4. R1, R2, R3, and R4 are all constants because all of those are just lengths of the length, right? Lengths of the links, man. They're just constant. Like this is this distance from this pin to this pin is never going to get longer as long as you turn this. It will never get longer because they are linked together at a certain point. They cannot get longer. So, it says, to solve the equation, we need to specify the value of one variable and solve for the remaining 2 variables. From this point forward, we reserve number 2 for the length whose position we will specify. So right there, what I'm telling you is that theta 2 is the input link, which means that we, as the people moving the mechanism, are going to specify the mechanism. We are going to specify how we are turning it, what speed we're turning it, right? And so theta 2 will be known based on us, right? We will know how fast we are turning it. We will know at what angle, the angular velocity we're turning it. We will know all of that because, well, we'll know, right? Just simply because we're the ones doing it. So that means that theta 3 and theta 4 are the only ones. And so use this as a rule. A rule is that R2 and theta 2 will always be the input link. So basically do not treat them as unknowns. Even though they are in a sense, like we don't know the value of theta 2 right now, right? But because we are the ones doing it, we do in fact know. It's kind of weird. It is a variable, but it's not unknown. You see my point there? Yeah, sorry. This chapter has a lot of information, so we are going to go over this a lot this week. So we'll get there. There's a lot of stuff to do. I know it's a big step up from the last chapter, which all I had to have you do was count. This is a little more than that. I'm afraid to say, but it is. There's a lot more to it than counting. So, all right. And so then it says, and reserve number 1 to be assigned to stationary links. So for example, number 1 in our question, this one right here, is a stationary link because it's just ground to ground, right? We're just connecting the grounds. These 2 ground positions are never going to move. They will always be this distance apart, right? So use R1s for grounds. So the rules so far we have, let's do 2 is equal to input 1 ground. So use those denotions. So like R1 and R2 are those respectively. So your vectors for 2 are the input link. Your vectors for 1 are used on the grounds, connecting the grounds. So be sure to remember that, because that is a helpful rule. Although sometimes there are more than one ground connections in a question, so that'll be another thing we'll get to. All right. And then it says it is time to introduce 2 more definitions. The input link, whose position is specified, and the output link, whose position is obtained by solving the kinematic governing the equation or the motion of the mechanism. Man, Therefore, equation 8 are two kinematic equations. Upon solutions of these two equations, the output variables theta 3 and 4 can be found for any specified value of the input. So, what it's saying is that this equation right here, these two equations right here, for any value of theta 2, let's say we put in theta 2 is equal to, I don't know, like 25 degrees or something like that. Let's say 25 degrees. You know, pi over, actually not even that. I'll just do it in radians. We'll do pi over 4. Let's say we put pi over 4 here, right? Because we do like to work in radians in this class. So let's do pi over 4. If you put pi over 4 here and here, you will get a number out, right? These two will get you a number because R2 is some length, right? It is a length. So a length times an actual number, you will get a number, right? So that pretty much, these two will now become numbers. R3 cosine theta 3 and R3 sine theta 3. This right here, cosine theta 3 and let's work up here. So cosine theta 3 and cosine theta 4. Those will not give you anything right now because we do not know theta 3 or theta 4, but obviously you guys know a little bit about solving simultaneous equations, right? Basically there is no difference here. So look at the equations right now. There is no difference between what we are doing here than what you have done previously. So for example, I'll just write this out in a different way. So if you take R2 cosine theta 2, I said that's a number. So let's just say it's 8. And then let's say the other one is 3, right? So I'm doing x and y. So this is y, this is x. So then it's 8 plus, now this is a variable. So let's do like, I don't know, 5 times x, right? And then plus, let's say this is 10 times y is equal to, or well, we have to do r1. r1 is some length minus 3 is equal to 0. And then if you do this over here, 3 plus 5, whatever, 5x plus 10y is equal to 0. So essentially, if you were to solve these two equations together, that is what you are doing in this terms as well. The exact same way. You are solving these the exact same way. It's just simultaneous equations. You just get rid of you just solve them simultaneous through an equation solver, or you can do it by hand, right? But obviously I'm not going to ask you to do that because some of these get to be really bad. And what I mean by that is you can have like, I think the biggest one I've ever seen, I think I've seen 10 equations and 10 unknowns. So that means you would have to solve 10 simultaneous equations to find 10 variables. So you would have to do that substitution or elimination for 10 equations. And I don't think any one of you want to do that. So essentially, we are just setting up equations. And I mentioned this last time. We are setting them up for them to be solved. So this right here, everyone make big note of this. This is what your exam will look like. You will put your answers in terms of this. So what I will tell you is you're on your exam, it will say, write the vector loop for this mechanism. Give me the equations, unknown. So give me the known variables, the unknown variables, and the scalar equations, right? So basically this is what your answers will look like. It'll say this is a known variable, although for this one right here, for our original one, you would say R2, R3, and R4, right? Because those were the links of the actual O and R1. So known variables are R1, R2, R3, and R4. Our unknown variables, theta 3, theta 4. And these are our x and y equations. So for your exam in 1 week, basically, this is what you will be doing. I will give you a mechanism. You will return me the number of knowns and unknowns and the scalar equations along with the vector loop. And that is it. That is all I'm looking for. But I know it's been a lot of information today. So we are going to start back next time tomorrow on a slider crank mechanism, and this I will have you guys do the vector loops for these, and we'll just kind of go through a few questions. Like we'll do this one, and we'll do another one. So we'll do this and another one, and we'll just try and increase the. Basically, I think it'll make more sense once you guys actually see a question. And once you guys do one, you'll see more of what we're trying to accomplish and how you make these vector loops. And then once we do a couple like easier ones and medium ones, we'll move on to a difficult one. Like, let me see if I can find you guys a really difficult one, just to show you what it looks like. Ooh, you've seen that one before. Yeah, like this right here. We're probably not going to ever do something like this, but this one, as you guys can see, has 3 vector loops. So that one is a difficult one. 3 vector loops, very, very challenging question. And I know. You know why I know? Because I was given this on an exam in this class. So I remember this question very well. But we will do something. All questions in this class will be like 2 vector loops or lower. I don't think I'm ever gonna give you a 3. So hooray for you. But with that, before you guys leave, let me get the attendance really